All right, welcome to this explainer. Today, we're literally peeling back the layers of the SHD-CCP engine to reveal exactly how pure, unadulterated mathematical logic can build an entire virtual universe from scratch. We are going to look under the hood of a system that honestly sounds like it was pulled straight out of a sci-fi novel, but as you'll see, it's actually an incredibly robust, fascinating piece of software engineering.
So here is our quick roadmap for today's breakdown. We're going to cover demystifying the engine, the micro, meso, and macro scales, the mathematical core, architecture and optimization, operating the virtual lab, and finally, real-world applications. Let's dive right in.
Section 1. Demystifying the engine and translating those terms.
Now you might hear terminology like holonomic cosmology or a central subsumption core and absolutely think we're talking about warp drives, right? But structurally speaking, this is actually a highly advanced parametric topology and multi-agent phase space visualizer. Basically, it's a high-performance engine built right in WebGL using the Three.js library. And its primary job? To model how incredibly tiny basic mathematical rules entangle themselves to form massive, overarching cosmic grids.
And get this, the sheer scale of time driving this whole visualization is just massive. The entire engine runs on a 25,920 frame sequencer. Now that number isn't just arbitrary. It actually represents a complete macro cycle, which is sometimes called a great year. So every single particle, wave, and cage you see pulsing in the engine, it's all perfectly synced to this one global clock.
Section 2. Micro, meso, and macro. Let's explore the scales of existence.
Okay, so the absolute crucial point to understand here is this nested hierarchy. At the very base, the microscale, we have just 3 individual agents, A, B, and C. Moving up a level to the mesoscale, we get 54 orbital nodes arranged in 3 intersecting rings, essentially representing an orthogonal hypercube. These nodes take the paths of our 3 microagents and weave them together into these massive braided trails. And finally, zooming all the way out to the macro scale, we get a massive volumetric environment. It's a 4x4x4 spatial matrix bounding reality itself, complete with massive toroids and a pulsating subsumption core. It all just cascades upward. To really grasp how that micro level works, we have to talk about what the engine calls governance. Imagine our 3 microagents as tiny little entities navigating along fundamental mathematical paths. You know, maybe a straight line, a toroidal loop, or even a complex trefoil knot. Well, governance is basically the mathematically constrained cage that twists around these paths. It dictates the strict rules of movement, causing ripples that eventually shape those pulsing icosahedrons and somatic energy lines all the way up at the macroscale core.
Section 3. The mathematical core. How we generate geometry on the fly.
So diving under the hood, we have the foundational geometry generator. It takes a single parameter, u, which simply represents a progression along a path from 0.0 to 1.0. You feed u into the equation, and it calculates and plots the exact 3D coordinate for complex shapes, like a continuous trefoil cannot. It is quite literally plotting the universe, coordinate by coordinate, frame by frame.
But here's the catch. Just knowing a point in space isn't enough, right? You need orientation. Think of this next concept exactly like a roller coaster track. If you're looping upside down on a twisted knot, the code needs to know exactly which way is forward, up, and right at that specific microcurve. By calculating the tangent, normal, and binormal vectors, the program allows those secondary geometries, like the governance cases we just talked about, to twist perfectly along the roller coaster track without breaking.
And to bring the whole thing to life, there's a function that modulates those base mathematical paths using high-frequency sine and cosine waves. By applying variables like amplitude, depth, torsion, and tension, it dictates exactly where those governance constraints are placed. This right here is what creates that stunning, vibrating somatic look across the entire engine. It is literally pure mathematical frequency rendered as visual energy.
Section 4. Architecture and optimization, the performance tech.
Now you might be wondering, building a huge spatial matrix full of pulsating geometric shapes normally requires massive computing power, right? Well, the system handles this using a really severe optimization technique called true draw batching. By utilizing something called instanced mesh in Three.js, it collapses thousands of individual objects into just a single GPU draw call. It stops the computer from having to render 1,000 separate cubes one by one, and instead says, hey, render this one cube, but instance it 1,000 times in these exact spots. Game changer.
And because of that incredible optimization architecture and draw batching, this entire multi-layered, completely math-heavy universe renders at a blazing fast 60 frames per second right in your web browser. No crazy hardware required.
The glue holding all this optimization together is the master render loop, the animate function. Think of the animate loop as the conductor of the orchestra. It moves the global frame forward on that 25,000 frame sequencer, recalculates all the mathematical phases, updates the 54 mesonodes, and perfectly triggers the final render to your screen. It just effortlessly keeps the micro, meso, and macro scales in perfect sync.
Section 5, Virtual Lab Operations. Let's run some experiments.
To really get your hands dirty and properly use the engine's interface, you should follow 4 simple steps. First, isolate your variables. Turn off the macro and mesoscales so you're zooming in on just one tiny microagent. Second, run a perturbation analysis. Take agent A, make it a trefoil knot, and just slowly tweak the torsion and tension sliders. Third, use phase space stepping. Pause the engine, manually drag time backward and forward, and watch the exact intersections. Finally, step 4, turn the meso and macro scales back on for emergent observation. You will instantly see how your tiny micro tweaks radically altered the massive woven rings all the way up at the macro scale. It's wild.
But a quick warning while you experiment in the lab. You absolutely must keep an eye on 2 distance metrics in the heads-up display. Manhattan distance calculates the sum of absolute coordinate differences from the center, while Chebyshev distance calculates the maximum difference. Basically, if you push your attention and torsion sliders too far and exceed the bounding limits of the reality matrix, the text on these metrics will turn red. That means you've triggered a theoretical structural failure or a total phase shift in your simulation. So tread carefully.
Section 6, Real-World Applications. Moving beyond the digital sandbox.
So why does all this matter? Because this engine handles complex Frenet frames, time phasing, and multi-scale hierarchies with such extreme efficiency, the underlying math can literally be adapted to major, real-world scientific disciplines. For topological physics, these exact knots and toroids model magnetic fields in tokamak fusion reactors. If you replace the math curves with steering behaviors, those 54 nodes turn into a massive swarm intelligence drone simulator. Swap out the circle loops for Keplerian equations, boom, you have an orbital mechanics engine for mapping deep space satellites. And finally, because it can all be frozen in time and exported, these parametric cages can actually be 3D printed for advanced generative architecture.
We've seen today how an incredible cascading power flows from basic micromath, like simple U-parameters and Frenet frames, straight up through the 54 mesonodes to generate absolutely massive macrostructures. By understanding how the SHD-CCP engine functions, you're essentially looking at the raw building blocks of emergence, which leaves us with this one fascinating question for you to ponder. If a single, tiny mathematical tweak can rewrite an entire virtual universe, what rule sets will you design for yours? Keep experimenting, and we'll see you in the next explainer.